In this lecture, we will talk about multiple capacitors in parallel. As we have shown before, we can put multiple capacitors in parallel. In this case, each capacitor shares the same voltage as others, and the total capacitance is just the sum of each capacitance. In order to achieve higher capacitance and achieve better performance over a wider range of frequency. In this lecture, we will focus on the AC analysis of the total impedance of the capacitors in parallel. This is an example from LM5036 evaluation board by Texas Instruments. It is a standalone half-bridge DC-to-DC power converter that can provide the isolated output voltage achieved by the transformer. If we look at the input terminals, we can see there are multiple capacitors in parallel. On the other hand, if we look at the output terminal, there are also different capacitors in parallel. Now I will give you the explanation. So this is an example of two different ceramic capacitors. The first one is 1 microfarad X7R, the size is 1206. It is plotted in yellow. The second capacitor is 0.1 microfarad. 50 volt, the same as the first one. Temperature coefficient is X7R, the size is 0805, which is plotted in blue. Both impedance and ESR are plotted in the same figure. The impedance has a letter V shape. At low frequency, 1 microfarad has lower impedance because it has more capacitance. However, this capacitor has lower resonant frequency around 7 MHz. For this reason, it is only usable up to its corner frequency. In contrast, 0.1 microfarad capacitor at lower frequency, it has higher resonant frequency. That means at higher frequency, for example, above 5 MHz, below 15 MHz, 0.1 microfarad is more usable than 1 microfarad in this case. LT by simulation. Now let's build the realistic models for these two capacitors. On the left hand side, this is 1 microfarad capacitor with ESR and ESL as shown in the schematic. On the right hand side, this is 0.1 microfarad capacitor with higher ESR compared with the first one and also a little bit higher ESL. So now let's do the AC analysis and plot the impedance of these two capacitors. This is the AC analysis of two capacitors. The first capacitor, which is 1 microfarad, is plotted in yellow. The second capacitor is plotted in blue. The results are matching with the KMAT results as we shown in previous lectures. The first capacitor has a resonant frequency about 7 MHz. The second one has a resonant frequency about 20 MHz. Again, the self-resonant frequency F0 is considered to be the maximum usable frequency for a capacitor. In this case, 0.1 microfarad can be usable up to 20 MHz. Next, let's create the impedance of two capacitors in parallel. This is a very commonly used capacitor configuration for switch mode power supplies. In this case, we add the parallel of two capacitors and we plotted the voltage shown in Vout3. The output impedance of two capacitors is plotted in red. It has 1 microfarad in parallel with 0.1 microfarad. As we expected, the overall impedance is lower than each capacitor, so that we can achieve a better performance over wider range of frequency, because we have lower impedance to cover more frequency range all the way up to 20 MHz. So it is more usable at higher frequency over 7 MHz. Also, we can achieve higher capacitance and lower impedance for wider range of frequency. This plot is coming from application note from TI. It shows multiple capacitors in parallel in order to achieve low impedance. We have multiple different ceramic capacitors and titanium capacitors in parallel in order to achieve low impedance over a wide range of frequency all the way up to 100 MHz. In this case, this is a particular example for a DC-to-DC converter, for example, a buck converter. When the frequency is below 10 kHz, the output impedance of this buck converter is majorly controlled by the closed loop, so that the output impedance of the buck converter remains below 0.01 ohm. Again, this curve is the maximum impedance limit. We have to guarantee that the overall impedance at output is below this line. To achieve that, we need to put multiple capacitors in parallel to have a wider range of frequency response to lower the impedance. If we have two capacitors in parallel and we only consider the ESR, we ignore the ESL. In this case, it's just two RC network in parallel. We can derive the impedance and the transfer function of the overall impedance. So you can see this transfer function. In the numerator, we have two left half plane zeros. In the denominator, we have an origin pole and have another left half plane pole. So in this case, it looks like a complicated impedance for this overall capacitor. Another simple case is if we have two identical capacitors, that means R1 equals to R2, C1 equals to C2. So overall impedance can be further simplified. Equivalent ESR just half of the resistance, and the total capacitance is 2 times C. Recap, in this lecture we talk about the benefits of putting multiple capacitors in parallel in order to achieve higher capacitance and also achieve better performance. That means lower impedance over a wide range of frequency. This is very useful when you have a higher operating frequency, for example above 10 MHz. We did some simulation in LT-SPICE to study two different types of capacitors in parallel. We can see that by doing so, two capacitors shows lower impedance over a wider range. Also, I show you the impedance transfer function of two capacitors in parallel. Here is the reference for this lecture. Thank you and see you next time.